Good day, everyone, and thank you for joining today's FOSA webinar. I'm Mike Hines, Chairman of the Fiber Optic Sensing Association. Today we've got a great show for you, providing a webinar that ties distributed fiber optic sensing technologies to applications in the rail sector. Presenting for us today are FOSA members Kevin Tribble of Frauscher, a rail sensing company, and Andrew Hall with OptiSense, experts in distributed acoustic sensing. Moderating today's webinar is Mark Unkefer, the director for FOSA. And behind the scenes, we have, working her magic as always, Joy Maloney, our eMedia director. Before we get started, I'll give a brief background on FOSA, who we are and what we do. Kevin, if you can change the slide. So FOSA is a trade association consisting of members who are involved with distributed fiber optic sensing. This could mean DFOS interrogator developers, fiber optic cable manufacturers, sensing systems designers, operators, etc. Our purpose is to promote the use of fiber optic sensing technologies in all markets. Our efforts to essentially provide high-level education to introduce these amazing technologies to those who may benefit from it. In addition, we provide monthly webinars like today's session, educational primers that can be freely downloaded from the FOSA website. That's www.fiberopticsensing.org. And we work very closely with lawmakers and regulators to the ends of raising awareness of DFOS to help the technology find applications where value can be had. With that, I'll turn the presentation over to Andy and Kevin for a look at how DFOS can be applied in the rail space. Thank you.
Thanks, Mike. So the outline of the webinar, we'll be looking at first introducing the fiber optic sensing now, how that sensing can assist railroads, an outline of some of the applications of DFOS within rail, how they can be implemented, and a summary of the benefits that can be provided. I now provide an introduction into the sensing itself. Distributed fiber optic sensing enables monitoring of fiber optic cables from a single location for a variety of different effects. We're looking at temperature sensing, acoustic sensing by monitoring vibrations, and strain sensing. The icons at the top of the slide will be shown throughout the presentation in the relevant areas. DFOS allows for continuous monitoring at high resolution with meter-size localization possible. And the fiber is the sensor. It's a passive sensor, so no power is needed. Multiple applications are possible from a single sensor, and it really is upgradable technology without replacing the interrogator units. Fiber optic sensing technologies provide applications across multiple industries. Pipeline condition monitoring is important for operators to understand how the assets are running. Pipeline heat trace monitoring is a special application in pipes that require crude oil to flow and heating to encourage that. Here it's important to monitor the temperature profile across the entire length of pipe. So temperature sensing is employed here. Third-party intrusion detection, if you're trying to monitor along the asset, you can very quickly pick up on any tampering or trespassing. Geotechnic applications, looking at seismic applications such as an early earthquake warning system, transport monitoring of both rail and road networks, oil and gas in-well monitoring service such as temperature profiling or vertical seismic profiling, industrial process monitoring as well, and structural health monitoring such as dams and so forth, where you can detect the fatigue of the structures. Areas on the electric grid, such as transmission cables, for example, that you want to measure temperature, it is fairly easy to do that with fiber optic sensing. The key benefits as they relate to railroad applications are it's a reliable method. There's little to go wrong with the sensor once it is installed. It's safe, a zero risk of electromagnetic interference from, say, signaling systems or track circuits. It's retrofittable. There's no additional equipment or infrastructure on the track or rolling stock. It's economical. From a per point basis, there is really no more economical method to do sensing other than DFOS over long length networks such as railroads, and it's scalable. You can run multiple fibers in a cable. In parallel, you can run acoustic sensing, strain sensing, and temperature sensing, as well as a communication backbone. So it is quite flexible in that way, and it's independent of the terrain and topology along the railroad itself. The applications can be grouped into three main areas: security threat detection, such as trespassing, threats such as fires, rockfalls or landslides, train tracking, asset condition monitoring of track defect, rolling stock and infrastructure, and we'll go into more detail in some of these areas later on in the presentation. So how is this data extracted from the fiber? The respective phenomena used to measure vibration, temperature or strain in a fiber optic cable relies on interaction between light and the glass within an optical fiber. The picture on the right shows the broad principle behind DFOS. DFOS technology sends a launch pulse of light into the fiber by an interrogator unit, shown as the red light pulse. A small fraction of this light is backscattered back towards the origin through interactions with the glass, which is shown in the green and blue. The backscatter properties change along the cable in accordance with the local environment, and different backscatter processes can be used to extract different information, which is typically processed within the processing unit to make into actionable information, which is then sent onwards to external systems or user interfaces. Now I'm going to show a short video just to illustrate this concept. So the fiber is interrogated by a launch pulse represented by the red pulse. And in this case, the train moving along the track generates vibrations represented by the blue crescents radiating out that can be picked up by the fiber. The backscatter from this is received, processed, and classification algorithms output the train position to the railroad operator. And now I'm going to hand over to Kevin, who's going to talk about how DFOS can help railroad operators.
Thank you, Andy. So one of the key things that DFOS offers railroad operators is the possibility to continuously monitor train movements, even in dark territories where conditional train detection equipment is not monitored. Trains are one of the easiest things for a DAS or distributed acoustic sensing system to detect. They generate a large pattern of acoustic energy that the system can recognize and follow as the train moves through space and time. No additional equipment is needed in the track or on the train to achieve this, because as we said, the fiber is our sensor. The DAS interrogator generates a light pulse and measures the backscatter as that's modified by the train sound applied to the fiber. An algorithm is then applied to the data, and this picks out the train signatures and tracks them, generating metrics like the real-time train position, the train length, its direction of travel and speed, and additional information like estimated times of arrival. And in addition to the basic algorithm, logic is applied around train behavior. So the system will recognize that trains might stop and therefore their acoustic signal disappears, but then if they carry on moving again from the same position, it's the same train. Equally, if there are areas on the track where the signal's temporarily lost due to the fiber location or fiber spools, we can maintain a consistent tracking ID through those. So here's an example of a train shown in a waterfall plot. So a waterfall plot is a useful tool to view DAS data. Essentially, it plots where the acoustic energy is on the fiber in space and time. And the color of each data point represents the intensity of the energy that we record. Hence, our train here appears as a diagonal stripe, from which the train tracking algorithm can work out its direction. So we see this one is traveling up in distance as the time increases, so it's moving away from our DAS interrogator. We can work out its speed from the angle of the diagonal, the length of the train by the width of the band of energy that it generates, and a position on the fibre at any point in time, which can then be mapped back to a position or a mile point on the track. So typically the front edge of the band of energy is our train front, and the rear edge will represent the rear of the train. If we took a slice through this waterfall at any point, then what we would see is the train signal as it passes a point on the fibre, effectively a time series. So we see the front and the rear and the band of energy that the train generates as it passes by. So in summary, the train tracking information can be displayed in a number of different ways, and the video you're seeing here now is an example of a graphical UI which shows the live position of the trains on the track and other information derived from the DAS train tracking data. But equally, the same information can be shared in a machine readable form with other systems. At the current technology level, DAS can reliably track trains, and this has been demonstrated in multiple applications around the world. However, there are some constraints. The performance depends ultimately on the cable position relative to the track and how the cable is installed, and we'll see a lot more about that later in this webinar. And since the system is essentially only listening to the train, determining exactly which track the train's travelling on can be a challenge, particularly where there are two tracks quite close to each other or through difficult junctions. Hence, additional logic, so determining the train track based on the direction it's travelling, etc., or inputs from other sensors such as wheel detection can be useful in this stage to fill in the gaps in the DAS data. Therefore, today's applications are non-vital, mainly traffic management information, so to find out how many trains are passing a certain point, to record and track train journey times, train speed profiles, detect unplanned stops, and generally find out where trains are where we don't have that information from a conventional signalling system. Also, platform announcements is another application of this technology, providing estimated times of arrival or warnings for passengers of approaching trains on station platforms. Importantly, though, as we'll see later, the train tracking is also an enabler for many of the other railroad acoustic sensing applications, as understanding where the train is at any point in time is key to understanding the data that we see from the DAS system. I'll hand you back to Andy now. We'll talk about the security and threat detection applications.
Thanks, Kevin. So DFOS can alarm on security issues and threats to the railroad infrastructure. For example, securing the railroad assets and infrastructure from trespass, vandalism, and theft, which is an important consideration for railroad owners and operators. Natural events such as falling rocks or landslides pose a substantial safety threat and cause significant problems for railroads, including risk of derailment and operational delays. Precise and reliable fire detection in enclosed spaces, such as tunnels and stations, is especially critical, as small fires can become dangerous very quickly. And now if we look at a few of the rail security applications that can be offered. So the first one is really the personnel detection of activity in protected zones, providing a corridor of protection along the fibre with offsets of typically 5 meters. And if you click again, Kevin, 16 feet, I should say, sorry. Or if you go back one slide. Sorry, Kevin, I thought there was an animation there. The sterile zone protection, this is on the top right, and this is where fence-mounted fibre optic provides complete protection in restricted areas from activities such as fence climbing and cutting. The bottom left is cable theft, where some of the copper cables which run trackside can be protected for alarm and events such as cutting and things like that, and theft. And finally, critical sites can be afforded perimeter security by installing a dedicated fibre spur surrounding the asset. Railroads run across all terrain, and their course typically encompasses a number of human-made structures such as embankments or cuttings, in addition to running through areas prone to rockfall or landslides. DFOS technologies can detect rockfall, landslide, and also significant ground movements. Strain sensing can provide information on landslide and subsidence, and can also provide a temperature measurement solution in parallel. So as well as monitoring the slope stability itself, if we have anomalies in the soil where it may be open and porous and we allow in liquids in, we should be able to see a temperature signal associated with that. With these insights, rail owners and operators can increase the safety and efficiency of operations. Now we're going to look at a case study of strain sensing where it shows the monitoring of a slope of about an angle of 45 degrees, which needed to be monitored for slope stability. If we look at the graph on the left-hand side, we have distance along the fiber on the x-axis and strain on the y-axis, with the line graph colors displaying data at an interval of approximately 5 days. And what you can see is a rapid increase in the strain over a given range of time as the soil begins to slide down that slope. On the right-hand side, it shows some examples of monitoring water ingress, which can be an indicator of soil erosion and potential slope failures. The bottom chart shows distance along the fiber and relative temperature on the y-axis. And again, each curve color shows a timescale of about 5 days for each color. And you can see clearly there's a trend there. And if we look into that into more detail on the graph on the top right, the thermal event location in red is compared against another location at a different spot along the fiber. And what you can see here is that temperature drop shows that rainfall percolated through to the fiber and created this localized cooling around it. Now, next case study is about a DAS system being used for rockfall and landslide detection. And here there was large amounts of rainfall which fell within a canyon, which initiated a series of landslides that caused significant track damage. There was no train in the area at the time, but some individual cars were parked within a nearby siding. The DAS system installed along the railroad generated alarms, which were sent to both the dispatcher and also announced over the voice radio to the nearest train approaching the canyon. This allowed the train to safely stop for the damaged track section. And finally, if we look at an example of fire detection within tunnels and stations. So here, a single DTS interrogator unit can monitor assets of typically up to 12 miles, and it can detect a fire localized to an accuracy of around 10 feet within a period of 1 minute. So it's a cost-efficient and reliable solution. It's approved in multiple countries, and there's thousands of installations. And in this example, it shows the Beijing Metro Line 5, which monitors 22 stations for fire detection. And I'll hand over to Kevin now. He's going to talk about asset condition monitoring applications.
Thank you, Andy. So most railroads face the challenge of how to maximize their track availability whilst the budget and the opportunity to maintain the infrastructure continually decreases. Achieving this obviously involves preventing failures, but also maximizing the useful life of the infrastructure. Hence, monitoring assets in support of a condition-based maintenance strategy is an increasingly relevant topic and another area where DFOS can assist. So in this section, we'll look at some examples of what the DFOS data can tell us about the condition of different railroad assets. For the track and fixed infrastructure, acoustic sensing of the wheel-rail interface can tell us about rail defects. Track bed issues can also cause some acoustic anomalies, or as we've seen, ground movement can be measured with dynamic distributed strain sensing. Flashovers or short circuits in overhead electrification also create a distinct sound, and these too can be recorded by DAS systems. For the rolling stock, wheel defects like flat wheels will change the train's acoustic characteristics, and this can also enable DFOS systems to detect anomalies with trains. So to start with track defects, a track defect in the DAS data shows up as a regular impulse or impact that's occurring at the same position in the track within the train signature. We generally get multiple impulses as a wheel traverses the defect. Depending on the train's speed and axle spacing, the periodicity at which we see the impacts will change. So in this waterfall example, we can see a broken rail, but a number of different scenarios can actually result in a very similar pattern. So typically these could be things like railhead defects, so depressions, cracks, or corrugations in the railhead. They could be rail breaks, as in the example we've just shown. They could be poor rail joints, so joints with a gap or a mismatch in rail height, which cause an impact to occur as the train wheel traverses. Could be loose fixings or missing parts of the track, such as fish plates or bolts that cause the track to vibrate in an abnormal manner. Or it could also be ballast voids or track pumping, which causes unusual or excessive vertical displacement of the track. But importantly, there are also infrastructure features like bridges and switches which create similar patterns, so these need to be taken into account. So here are two real examples of track defects. A broken rail at the top, which occurred under testing at the TTCI facility. The plot here shows the successive train journeys in time versus distance, leading up to the detection and alarming on the rail break here. The second example from a different site is a rail surface defect, in this case resulting from a crushed railhead at a previously welded location. So maybe not requiring immediate attention, but something that can be found and monitored with the DAS technology. To monitor the condition of the track, there's typically a four-step process that we follow. The first step naturally includes installation, but also tuning of the system to the fiber characteristics on a particular site to make sure it can reliably detect anomalies and defects under the train, and georeferencing of the system so that the fiber location can be mapped to a track location. The second step is then to record what we call the natural pattern of life on the track, to understand the normal train signatures and where defects and anomalies normally exist in the track. Next, the system is informed about the existing defects and track features. So for example, here we have a bridge which causes a unique signature which looks in some ways similar to a rail defect, but we know here that it's not because it's part of the bridge, and therefore we can tell the system that this is a normal infrastructure feature and a certain amount of defect reports are normal, and only to warn us if those suddenly increase or change. So this is normally an iterative process between the railroad and the DFOS provider. It will involve looking at the locations where we see defect type reports, correlating those with things like switches or bridge locations, and it might even involve inspecting the track to find out what defects are already present and which state they're at. But once these steps are complete, we should have a baseline from which we can monitor and alert for new defects, essentially a starting point for long-term monitoring. So moving on to wheel defects. In a similar manner to the track defects, wheel defects like flat wheels can be identified in DAS data as impulses that occur regularly within the train, except this time they're moving with the train rather than happening at a discrete point in the track every time. The frequency at which impulses occur for wheel defects is a function of the train speed and also the wheel diameter. So in this example here, we can see it within our train signature. We have the front of the train, the rear of the train, and then a regular impulse indicating that this train has a flat wheel within its consist. So the goals are to provide flat wheel alarm, but also to accurately localize the flat wheel along the train. So we know the train length, we know where the head of the train is, and we can therefore report where the flat wheel occurs in relation to that. And as a distributed monitoring system, we can also add data about where wheel defects are seen. For example, we can determine if a defect occurs only in a right-hand curve or a left-hand curve, or maybe only presents on straight track. Another interesting DFOS application in asset condition monitoring is the localization of short circuits in overhead electrification systems. So as used on some passenger and urban lines. Shorts or flashovers in the electrification system, like the one shown here in the picture, can occur when insulating components fail, and they can take out power on large sections of the track. Hence, a single incident can have a big impact on track availability and train services. The sudden loud arc that occurs when a flashover happens creates a distinctive acoustic signature, so the V-shaped pattern that we see here. And this allows the DFOS system to pinpoint the flashover location to a much higher accuracy than existing systems. So the power system will obviously tell the operator that power's gone down, but that may be a section that could be several hundred yards or more, whereas the DFOS system can narrow that localization down to a number of feet to know where the flashover has occurred, and therefore this means that inspections can be targeted to the right area and the power outage time can be reduced to get the track back in service and obviously save money. So how simple is it to deploy fiber optic sensing within the railroad? For all the DAS applications discussed, spare cores in the railroad's existing communication fibers can normally be used. This means that sensing can be achieved at very low cost and also importantly has no impact on operations, so we don't have to go into the track and dig up things or move things or disturb existing equipment and systems in order to install a DFOS monitoring system. For some applications like fire detection or geohazard monitoring, or where sensing is part of a new infrastructure project, it might also be possible to specify a new fiber installation, and then as we'll see later, we'll be able to choose fiber types which optimize the system performance. In terms of DAS, performance is best when the cable is close to the target sound. So if our target sound is a train, we want to be 10 to 15 feet from the track to pick that up reliably. As well as location, the installation method also has to be considered. So the fiber, existing comms fiber, could be in a number of scenarios within the track. So in the picture here, we see buried fiber, which is fairly typical. Also fairly common is fiber that runs alongside the track in a concrete conduit, or fiber which is mounted on a tunnel wall, possibly even on the overhead catenary system itself, and maybe rail mounted or on top of the ballast. So each of these have their own unique challenges. Buried fiber normally performs quite well. It gives good coupling to the ground, some protection from background noise. Fiber in concrete conduit is similar, but obviously fibers which are just exposed to the elements on the rail or on the ballast can be subject to wind and rain noise, and also can be broken fairly easily by maintenance activities or train movements. We also have to consider that the location and installation method will change at different parts in the track. So we see here a tunnel with the fiber mounted on the wall. It's not at all unusual to find that fiber may be mounted on the wall in tunnels, but it will then revert to being in conduit or buried when it exits the track, and it can change location and installation method several times over a monitored area, for example, at bridges or tunnels. Further information on the railroad installation considerations and the type of things which can or need to be taken into account when planning a DFOS install in the railroad can be found on the FOSA website at the link given in this slide. Cable type is also a factor in sensing performance. So for acoustic sensing, the requirements are single mode fiber with good acoustic coupling to its surroundings. So what that means essentially is single armor or an unarmored cable. So the unarmored cable you might find in conduit, single armor for direct buried to provide a degree of protection and also rodent resistance. We want a tight buffered or gel filled cable so that the sound transfers from the outside of the cable to the glass fiber itself. And often the existing communications install in most scenarios comes close or matches this spec, which means that existing fibers can be used without additional cost or groundworks. For strain sensing or temperature sensing systems, existing backbone in the two most common types can also be used. So the loose tube, gel filled, single jacket cable, often found in conduit, can be used to good effect. Also the armored version, which is often in a buried situation, can be used. And for special deployments where new cable can be specified, there are other options that can be considered to give improved strain and fiber coupling. So in terms of optimal installation methods for the applications we've looked at today, direct buried is normally the best choice. So it gives the best results for train tracking and ACM if positioned well relative to the track. It's also good for distributed strain sensing and detecting third-party intrusions close to the fiber. Concrete conduit is a close second, so it's generally very good for train tracking and condition monitoring. And it's also good for providing theft detection of co-located cables. So if there are lots of high-value copper power cables in that same conduit, then having the fiber there is a great way of detecting people who are tampering with those cables or attempting to steal them. Wall or fence mounted cable is not so ideal for the train tracking and asset condition monitoring applications. It can be used, and it's possible if wall mounted in tunnels and the background noise levels are low. However, where it is good is for fire detection in tunnels, and also for some of the security applications, so detecting impacts that occur or affect directly a fence, so the cutting or climbing of the fence, but it may not be so good for detecting walking patterns. We mentioned rail mounted before. This you'd think could be a good scenario for train tracking, but actually it presents its own unique challenge because the fiber will be subject to huge vibration both before and after the train passage. And also there's a very high chance of fiber breaks. It's generally poor for the security applications too, although we have found that you can find people who are walking directly on the ties using rail mounted fibers. But generally it's a fairly rare installation scenario. So in the majority of DAS applications discussed today, fiber is best located in the general right of way. And this slide illustrates where we would ideally put it. So for buried fibers, our preferred scenario, the recommendation is 3 to 15 feet from the center line of the track and buried in the soil at a depth of 1 to 2 feet. So buried cable should be bedded into the soil to provide good acoustic coupling, infilled with the same soil type and compacted. Again, much more information on installation considerations for different DFOS applications can be found on the FOSA website. So to finish off today's talk, just a quick summary on the benefits of fiber optic sensing. So with DFOS, there are a number of unique benefits that combined really add value for railroad sensing and monitoring applications. Large areas can be covered in real time. So 80 kilometers of fiber monitored from a single location is typical, and the system can scale to create a sensor network monitoring a whole infrastructure. Events can be located accurately down to a number of feet to guide maintenance or inspection teams to the right place. Most importantly, no equipment needs to be retrofitted to the track or rolling stock, so disruption to operations is kept to a minimum. The fiber is our sensor. In most cases, that's already part of the railroad as the communications infrastructure, so setup and maintenance costs are very, very low. The fiber itself is maintenance free pretty much, and the equipment that is used for the sensing is also very low maintenance. And importantly for the railway, there are no real safety concerns, so there's no risk of this system interfering electromagnetically or in any other way with vital signaling or power systems, and therefore no safety implications or complex safety case documentation that we need to consider. So per sensing point, as we said, there's really no more economical way to monitor lengthy critical assets like those you'd find in the railroad. So to round off today, here are some of the FOSA members who've contributed to today's webinar and are active in fiber sensing for railroad applications. Thank you very much for your time and attention today. I'll hand you back now to Mark.
Thank you very much, Kevin and Andrew, for the presentation. To ask a question, there's a box on the right hand of your screen, and one of the options is to ask a question and type that in, and I will pass that on to our two presenters. But to kick things off, I wanted to ask, how much has DFOS been deployed in North America by railroads so far?
So good question. So in North America, I would say it's certainly one of the front runners for DAS, with systems deployed for rockfall detection and a number of trials with Class 1 railroads and urban operators for train tracking and asset condition monitoring applications. There has also been a few DTS deployments for fire detection as well.
That's helpful. In listening to some of the presentations elsewhere on rail safety applications, I was struck by the fact that was raised that the primary source of fatalities, as I recall, for that occur on rail right-of-ways is with trespass, with unauthorized intrusion, and you mentioned that as really being one of the applications that is available for that. You also mentioned that this is being deployed in urban areas. How much of a factor is this trespass prevention an issue for, or a benefit that is being used?
So in terms of the issue that it causes, so there's a few areas. I mean, the intrusion into the right of way. We've seen that certainly in areas where you have high-speed lines, or if you've got freight corridors where they're going through sort of critical areas where they have got physical barriers up. It's always important to be able to afford protection in those corridors, and certainly DAS, can provide a key piece with that to be able to detect people walking around the fiber. And sometimes it can be used as a complementary system to within overarching safety systems that might include, or security systems, sorry, that include cameras or other technologies as well.
Also,
Sure.
DAS, because of the long reach of the system, can actually identify areas where trespass might be occurring, hotspots, for example, where people are accessing the track that the operators may not be aware of initially.
That's helpful.
Yeah, and it can influence as well the decision making on whether signage is put there, whether further gates have got to be put there, or whether security patrols got there more frequently.
You referenced other systems. Can you give examples of the typical external interfaces of the information from DFOS into the railroads?
Yes, so alarm information can be passed to SCADA or alarm management systems. Email or SMS alerts can be passed on in the case of threat detection, or we can share information in a machine readable XML form to go into other dashboard type systems that want to display real-time or monitoring information from different sources.
And this probably, I think, was a little bit covered, but maybe it needs some more explanation. How is the fiber distance reference to track location?
Okay, so this is something that's evolving. One way to do it is to send people into the track to do what we call tap tests, so we could make a distinct tapping sound or noise at a particular point on the fiber that we know relates to a particular track mile point. And then we do a number of those and interpolate the results to basically map our fiber position to track position. Also, it can be done with GPS, so we could put somebody on the train with a GPS receiver, and then we can time sync the GPS data to the signal that we see from the train on the fiber, again with some interpolation where we might lose the GPS signal, or we may have areas where we lose the train due to spools or something on the fiber.
And here's a question about the cable. What is the average life expectancy of the cable on, again, on average?
So that's so that question, it's approximately about 20 years is when a lot of people look to say that, you know, that's when it's guaranteed the life for. But then, you know, what has been found is that certainly for DFOS technologies, that we have been connected to fibers in excess of that. And for us, you know, it's still performing well, and they're still being used as the communication backbone for the customer too.
Now, this is a question, I'm not sure if it's referencing just the fiber or other systems as well, but the question is how many types of sensors do you deploy for the numerous sensed conditions that were mentioned?
I think for all the applications we've talked about, the fiber itself is the sensor. Right. Different techniques might be applied, so it's probably quite a technical answer, but different types of backscatter are modified by different types of parameter like strain or temperature. So there may be different optical techniques used in the interrogator, but in terms of sensors, it's always a fiber of some description.
I think that's always one of the points that is a challenge to drive home, is the idea that the fiber itself is the sensor and doesn't require sort of additional systems. They may be used complementary, but the fiber itself is the key. So the next question is, are there any special requirements for the fiber, types of connections or numbers of connectors that are necessary for to prevent optical loss?
Okay, so from a DAS point of view, there are some conditions. So what we would typically do as part of a survey process for any new project would be an OTDR trace of the fiber. So first of all, we pick a spare fiber that's not being used for comms. We do an OTDR trace on that, and generally we're looking for a total loss of less than 10 dB along the whole length of the fiber, and no significant losses or reflections at any joint. So no significant events there of more than 1 dB. The fiber also needs to be terminated so that the light passes cleanly out of the end without reflection. So we have a special termination unit that we might put on at the end of the fiber. And where there are connections, generally we prefer angled APC type connectors because they don't create reflections. So specific requirements will differ between the different technology types, but what we're generally looking for is a good condition fiber with low optical loss.
And this is maybe another clarification questions about the need. Do the sensors, again, the fiber, require any special power? How do you address
that? Do you mean optical power?
I think it's really kind of a clarification that. Okay. You don't need, I could answer it, but the question was, do you need a power source? And I think you can probably address that yourselves.
We need a power source for the interrogator and processing equipment that's fitted locally on track, but that's typically, 500 watts or less. It can go in an equipment room or a communications room, but there's no power required outside of that one location, so we don't need any power locally in the track or anything like that. Right. It's just one unit.
Correct. Can forgive me, I've been through these a couple of times. Can DTS and DSS, temperature and sense and sound, I think they mean DS. Well, DSS, I think they also mean DAS, be measured on the same cable or fiber? I think strain. I guess the question is really, can all the different applications, so sensing, strain, and acoustic, all be done on the same fiber?
So on the same cable, they can use different cores within that. So if you had a 12-core fiber cable, then each of those different interrogator units would connect to an individual core to provide that.
Another fiber question. How does this is given that the fiber is the sensor, how does this sense when there's a directional bore under waterways when the rail goes over a bridge? So I think that's a question that's really kind of an installation question you can address.
So for us,
so the issue, I think the issue that the case that's being asked about is where the fiber may be going under a waterway while the rail goes over a bridge.
Okay. So in that particular example, what you would have to do would be that you can zone different areas of the fiber so that you can change the parameters there or to disable functions. So in that particular area, then that particular area would be zoned out and the functions would be provided either side. But typically when a railroad passes over a waterway, the guidelines that are given for the laying of fiber is typically on that overpass itself or the bridge that goes over. So the fiber is within the superstructure itself.
I got sort of another, how shall I say, clarification question regarding fiber. So what is the frequency of the placement of sensors along the route, and therefore the number of times of access to the fiber optic cable? And does this approximate the existing wayside access? So I think we need probably another clarification about how the fiber optic cable works.
Basically, the fiber is the sensor. It's a continuous sensor. So although the data may break down into thousands of discrete locations, it's a continuous sensor. In terms of accessing it to install the equipment, we need to access it at one position where we inject the light source. So that could be in a patch panel in a communications room. And then the only other place where we would need to access the fiber, assuming that it was intact and in good condition, would be at the very end of the range in which we want to sense, where we'd want to terminate it such that we didn't get any reflections if we were reaching the end of the fiber.
To give an overlay on a network system, if you were looking at a railroad, say of 130 miles, say, what you could have would be that you would have two locations where you would have equipment which the sensing units would point in each direction, and then they would be networked together. But across that area, you would only have two sites that you would have to find. There is a bit of variation, as you'd imagine, between the technologies with some of the ranges that that they would go. But broadly speaking, that's how it would be, but for a network system.
Well, this comes close. I guess the question, again, a little bit of a fiber, but what is the expected average cost of repair of any point along the track? So I'm assuming that's an issue about whether there's a break in the fiber. Maybe you can address that or how that gets addressed.
Yeah, I mean, that would be the only instance in which a repair would be required, but I guess the cost would be very subjective depending on the costs of accessing the site and the particular installation scenario of the fiber that was there. I guess difficult one to answer.
I guess it's specific really to the kind of break, but yeah.
But generally there's no maintenance or repair involved unless the fiber's broken, and we find that the fibers only generally break due to external factors, so some maintenance work or somebody digging or doing other related work that damage the fiber as part of that.
It may be part of a broader problem. Are there any international standards that define the specs of a DAS system, and in which country are they applied?
So I think the answer to that is that I don't think there is any industry standards for the system themselves. There is working on sort of standards in specific application areas, and we also state, what sort of standards that, certainly for DAS systems, are needed in terms of the telecoms fiber itself.
Quick question about the frequency at which calibration has to take place. I guess they think this actually is on the system rather than the fiber. So how often does that have to be, the software and what have you, be adjusted?
I think generally there isn't a calibration process. Once we've set the system up and tuned it, it should just operate continuously in that fashion as long as the characteristics of the fiber don't change over a period of time. Obviously, if some work takes place and the fiber characteristics are changed, then retuning may be required, but I don't think there's a regular requirement for calibration.
Good. I think that brings us up to the end of our questions, and so I wanted to thank you guys for a very informative presentation. I think we've probably exposed a lot of people to the sort of unique characteristics of fiber optic sensing, how the fiber itself is the sensor and how it has some durability in long-term use. This actually will be our last webinar for the summer, but we will be kicking off, FOSA will be kicking off 2 webinars in September. We will have on the 20th, September 20th, FOTEC and network integrity on September 27th. Keep track of our website and we'll keep you posted for additional information. Kevin, Andrew, thank you very much for a very useful presentation. One last point. Usually a question we do get, all of this will be available online at our YouTube site, but also on the Fiber Optic Sensing Association site. So you can download and listen to it or refer this to your colleagues at your or their leisure. Thank you very much.
Thank you.
And this concludes the broadcast.